Hi, welcome to the first lecture of the semester. How do we describe and visualize motion? This is going to be sort of really conceptual, but a foundational sort of lecture that we're going to introduce the words we use to describe motion, what they mean, as well as a technique to help visualize motion. So when we're addressed with trying to study kinematics and how things move, we're all on the same page and have a good language sort of to cast those problems in. So the first question is, start of the course, where the first section is kinematics, the study of motion. How do we describe motion? We're scientists, physicists. We're going to have to be quantitative about this. We're going to have to put numbers to different things eventually for these to really serve their purpose. So we have to be really specific about how we describe motion. Words have to have very well-defined meanings. We can't use some sort of wishy-washy language we might in everyday casual discussions. So what we're going to do is we're going to focus primarily on three words that, or concepts, if you will, that to describe motion. And they are position, which is where something is, a velocity, which is how that position changes in time. And the last one is acceleration, which is how that velocity changes in time. And these are our sort of primary definitions that we are going to use to describe motion. I'm quite certain most of you have heard of these words before. You've probably used them in everyday discussion. As we're going to see in the first few lectures, though, some of the ways we use these in everyday language are going to be slightly different from how we use them in physics. One of the major ways they're different is these are all vectors, which means they have direction. And in everyday language, it's rare that I think when you use a word like velocity, you're explicitly trying to describe that direction as well. But we'll cover that more as we go along. For now, let's just focus on what these words mean, position, where it is, velocity, how that position is changing in time, and then acceleration, how that velocity is changing in time. All right. The next thing we're going to want to do is we're going to want to know how to visualize motion. So how can we visualize motion? Let's say I described some situation, I'm standing on a pitcher's mound and I throw a ball towards the home plate, whatever, and you want to we're going to be trying to describe the motion of that ball, and you want a way to visualize that. You're sitting there and you have your paper and pen and you're trying to analyze this situation. One way we can actually do this is through what's called a motion diagram, right? It's a great way to visualize motion just on paper, and it sort of uses the same thing that we would do if we were to try and make a movie. At least the way movies work is you basically just take a bunch of pictures really quickly of a scene, right? So still photographs. So, with the old cameras with the actual film going through, you take a bunch of images evenly spaced in time. So let's say, take first picture, wait a tenth of a second, second picture, another tenth of a second, third picture, another tenth of a second, that picture. And then if you were to play those, show you those pictures at the same time intervals, it would look like this car was actually moving to the right. One of the ways we can do this, we don't have, we can't make movies on our paper, but what we can do is we can get the same idea where we can draw sort of pictures evenly spaced in time and overlay them on top of each other to make one picture. And it would look something like this, where we have some skateboarder rolling to the right, and if you were to draw that skateboarder at certain times, so at 0 seconds, 1 second later, 2 seconds later, 3 seconds later, they would, perhaps look like this. And you can get a sense of how that motion diagram captures a lot of the idea of how that object is moving. I mean, if it went the same distance in between each image, so these were a second apart, it's gone that far in 1 second, and then in the next second it went the same distance, and the next second it went the same distance. You can tell that that skateboarder was moving at the constant speed. Likewise, if you had a motion diagram that looked like this, you could immediately, just from looking at it, get a sense that that person is speeding up, right? They when a certain distance in the first second, larger distance in the second, third, even larger in the third second. So you can see that they have some acceleration. Their speed, their velocity is getting larger as they go this way. And you can capture all of this sort of in a what we call a motion diagram, which is one of these things, just a series of images of that object at evenly spaced in time overlaid on one sort of image. So let's think about this in practice. So what I'm going to show here is a video just of someone walking by. And I want you to think about that motion and describe what you think it looks like to yourself. So there it is again. Now, if I show a video like that to most people, what are they going to say that, how are they going to describe that motion? Now, if you're like most people that I've asked these sorts of questions to, they all come up with essentially the same sort of description, right? We have a person walking to the right, roughly constant speed. What you won't hear people describe is, I never hear people initially start to say, well, he's swinging his arms right to left, he's sort of kicking his toe up as he walks, or any of that. The reason is, most of us acknowledge that if I'm asking you to describe how that person was walking across, there's a general idea I'm trying to get. How did that person move across that scene? I'm not asking about the internal details of what that person was doing. We didn't care. You kind of intuitively knew. I wasn't really concerned with how their hair might have been bouncing in the wind, or what their gait was specifically like. You identified the core idea of what we wanted, and intuitively sort of used what we call the particle model. And that's what we're going to use for most of this course. Way later in the course, we'll start to add to this. But for now, we just use the particle model, which is a beautiful way to simplify things so that they can easily be analyzed. The gist is, things are complicated. Describing how that person walked across the road was complicated. Their arms were swinging, their legs were taking strides of a certain size, all of that, but we often don't care about all those internal details. So what we do is we describe the motion of whatever object we're looking at as if it were just a single particle, one mass at a single point in space. So it has one position, and then we're going to describe the motion of that position or that particle through space. This has the benefit of a lot of things. The big, most important one is it simplifies things to a level where it makes it much easier and very tractable to quantitatively analyze these situations, but still give extremely accurate and very good results. So let's look at a example of a motion diagram and see what we're looking at. So we have some cart moving through space. I make a motion diagram using the particle model that looks like this. And my question for you is, which direction is the cart moving? So now that you've had a chance to think about it, I wish these were synchronous so we could actually get some feedback on what you're thinking. But let's go through these answers. If you think it's moving to the left or right, what would you have had to have assumed, right? If this is going to the left, I'm essentially assuming I start here and then I start speeding up to the left. But how is that really any different than if I'm going to the right but slowing down and coming to a stop? The point is, for this situation, there's not enough information to tell. We don't know everything that we need to really make use of this motion diagram. The part of information that's missing is something with respect to time, the order that these images came in. If we know, as soon as we know which dot came first, second, and third, or fourth, or fifth, we can then begin to describe that motion. So how does this motion diagram actually work? How can we use it in a specific case to sort of capture everything we can about the motion we're trying to describe? So let's look at a little example of just a car pulling away from a stoplight. All right. So how is that going to look? Well, we've all seen this happen before. Car stopped at a stoplight, light turns green, it accelerates, speeds up as it goes away from the light. So we're using the particle model, thankfully, so I can just draw my car as a particle, just a little dot. Makes life really easy when you don't have to draw those details. This is where the car starts, light turns green, it starts to move to the right after a given amount of time. It's moved, say, that far. The same amount of time later, it's gone a little bit farther because it's speeding up. Same amount of time later, even farther, and so on across. We could continue this to the right as far to capture as much of the motion as we want. But for now, those 4 points are enough. And that's the basis of our motion diagram. Now, we just saw in the question that we just asked, we need to know the order of these dots, like which came first, second, third, and fourth. Obviously, I just drew them, so we know that. But imagine yourself just handing a completed motion diagram to someone. We're going to need some way of indicating that order to them. You can number them, 0, 1, 2, 3, 4, however you want. There's no real rules that we must follow. I prefer to just sort of label the times that they occurred at. So, this was the initial time, t0, and then some later time, t1, the second time later, t2, and then t3 there. So each one of those times separated by the same amount, so say 1 second each, or however, we're not putting numbers to this right now, but evenly spaced in time. And that's sort of a working motion diagram. Turns out there's a lot more we can get to this. I mean, we can conceptually just sort of see that it's speeding up to the right, but remember, we're going to try and use the words that we introduced at the start of lecture: position, velocity, and acceleration, to describe motion. And we can actually have all of those indicated and labeled on this motion diagram, believe it or not. So let's start with position. All right, this is a one-dimensional problem. We're moving in a straight line. So let's call that direction x, and we'll label position, that variable, as x. And we're going to do the same sort of thing. Just label the position of where these dots are: x0, x1, x2, and x3, right? And that's pretty clear. Positions, remember, our definition is where something is, so we've just indicated those dots are, visually where they are. We've labeled them. What's next? Well, velocity. So recall, what was our definition of velocity? Well, it was the change in position with the change in time. So how much did it change? Well, if you look at this first change in time from t0 to t1, our position started here and changed to there. So we could draw an arrow showing how our position changed between those two positions. We can do the same thing here. We can do the same thing here. So we've just drawn how the position changed in between each of the positions that we had previously labeled. And it turns out, if the velocity is just that change in position over a change in time, the change in time between each point is the same. This delta t, we use the symbol, this triangle, the Greek letter delta, to kind of mean change. So this change in time was, say, 1 second. So was this change in time. And so was this change in time. So if the change in time is the same between all of these, the change in position that we've indicated by that arrow is actually a good representation for the velocity. The change in velocity is going to be directly proportional to that change in position. So those velocities are actually well represented by those arrows. So I can just label those as well. We have small velocity here, getting bigger and bigger as we knew when it was speeding up. So that's great. We now have a visual representation of our velocities, which include both how fast it's going and which one's faster, and the direction it's going. The arrow points in the direction it's going. The last thing we need is the acceleration, right? So if we think of what our definition of acceleration was, it was the change in velocity with respect to time. So how did the velocity change when I went from v1 to v2? Well, if you want to figure out the change in anything, you take how much did it change going from an initial thing to a final thing. You take the value at the end, the final, and subtract from it the initial. So the acceleration is essentially going to be the change in velocity between v1 and v2 is going to be v2 minus v1. And written another way, we can consider that v2 plus negative v1. Now, what does this all mean in terms of this visual representation in the motion diagram we're trying to draw? Well, think about what v2 is. We've driven v2 as an arrow, right? And we've drawn v1 as an arrow here that looks like this, v1. If I wanted negative v1, that negative sign is essentially just going to flip that arrow. So if that's v1, negative v1 would look like that. So if I want to know that change in v, which is v2 minus v1 or v2 plus negative v1, I can just sort of do this add the arrows together idea, which would be v2 takes me from my starting point to here. And then if I add negative v1 like that to it, I'm going to end up with the resultant change in velocity, that delta v is going to look like that, from where I started to where I ended up after following both those arrows. So if I do that and add it to my motion diagram, I have a v1 or a delta v that looks like that. And then if I go between these two velocities, v2 and v3, how did it change there? I'm going to get the same sort of thing where that's my change in velocity between those two. And since acceleration is the change in velocity over some change in time, these are essentially my accelerations, right? And we can label them. So again, what we've got is this motion diagram. Now I've drawn a lot of detail on it. I guess I could erase this delta t's because they're kind of all implied, but we've seen what we see here is this is kind of a nice qualitative map of everything we've got in this problem, right? I've labeled all my positions, so I know that they're going to be changing and getting more to the right. I've got my velocities all represented by these arrows. I can see immediately that they're getting larger, so they're, and all pointed to the right, so it's speeding up to the right. And, that's also indicated by these accelerations that I've added in there. So again, a good motion diagram contains a lot of information about the problem. Right now it's all qualitative. We haven't added any numbers to it, but it's still going to be very useful to sort of guide our quantitative reasoning when we get to that point. So for now, that's how we do it. It's a good idea to practice these with homework or whatnot. Next lecture, we're going to go into, okay, let's add some numbers to this and start to get sort of quantitative about how we're going to put numbers to position, velocity, and acceleration.